Ask 5 experienced technologists to define the lab mean on a QC chart, and you'll often get 5 subtly different answers, and none of them are necessarily wrong. The phrase legitimately refers to at least 3 different numbers, and mixing them up is one of the most consequential mistakes in the discipline. Candidate 1 is the manufacturer's assigned mean, the target value printed on the QC package insert, derived from the manufacturer's own multi-site validation testing. Candidate 2 is the peer group mean, the average result every other lab running the identical instrument and reagent lot reports into an interlaboratory comparison program. Candidate 3, and the one your Levy-Jennings chart should actually be built on, is your own lab's cumulative mean, the empirically observed average of your QC results on your instrument run by your staff under your real operating conditions. This is the only one of the 3 that reflects your lab's actual performance. These 3 numbers routinely disagree, sometimes meaningfully. A manufacturer's insert might list a glucose control target of 100 milligrams or DL. The peer group running the same analyzer might average 102, and your own lab's first month of data might center closer to 98. 3 defensible numbers, 1 QC chart to build. The hierarchy that actually matters. The manufacturer's mean is a starting reference, useful before you have your own data. The peer group mean is a comparability check, telling you whether your lab is drifting relative to everyone else. But the working target on your daily chart should always converge toward your own cumulative mean. Confusing target value with expected lab performance is exactly how false rule violations creep in. If your chart is still centered on a manufacturer's insert mean your instrument has never actually matched, you'll flag warnings on results that are perfectly normal for your system, and technologists will start distrusting the chart altogether. This is precisely why CLSI guidance is explicit on the point. The manufacturer's insert mean and SD should only ever be used as a provisional placeholder for the first few days of a new lot, never as the permanent target once your own data exists to replace it. So before any conversation about updating the baseline makes sense, the first job is establishing that baseline correctly in the first place. And that starts with a very specific, statistically grounded protocol for how many data points you actually need before you can trust a number at all. Every new QC lot starts from 0 data. CLSI's answer to how many results before I can trust a mean is specific and non-negotiable. A minimum of 20 data points, collected across at least 20 separate analytical runs, before a preliminary mean and standard deviation are calculated at all. 20 separate runs, not 20 replicates in one batch. That distinction matters enormously. Running the same control 20 times in a single afternoon captures only within-run variation and misses the run-to-run, day-to-day, and calibration cycle variation that actually shows up in routine testing. The math behind why 20 is the floor, not an arbitrary round number. Standard error of the mean shrinks proportionally to the square root of n. Going from 5 to 20 points cuts your uncertainty around the mean by more than half. Going from 20 to 100 only shaves off marginal additional precision. The SD estimate is the fragile half of this calculation. With only 20 points, the standard deviation itself carries real sampling uncertainty. A single unusually high or low run early in the collection window can meaningfully distort the calculated SD, which then distorts every Westgard rule built on top of it. This is exactly why CLSI recommends treating the first 20-point mean and SD as preliminary, not final. The lot goes live for daily monitoring using these numbers, but the lab commits to recalculating a more robust cumulative mean once another 20 to 30 points have accumulated on top of the initial set. A worked example makes this concrete. 20 consecutive potassium control results with a preliminary mean of 4.02 mol, or L, and SD of 0.09. That SD sets your plus or minus 1 SD, plus or minus 2 SD, and plus or minus 3 SD lines at 3.93 or 3.84 or 3.75 on the low side, and 4.11 or 4.20 or 4.29 on the high side. The entire Westgard rule structure for the next month rests on this one calculation. Practical timing matters just as much as the math. This 20-point collection has to happen while the outgoing QC lot still has valid shelf life remaining. Starting it only after the old lot has already expired leaves no runway to catch a problem with the new lot before it's the only material on the shelf. So a baseline mean isn't something you eyeball from a handful of early results. It's a specific, 20-point minimum statistical exercise with real mathematical justification behind the number. The next question is what you do with that preliminary mean as more data keeps arriving. Once your preliminary 20-point mean is live, you have three genuinely different methods for how that number evolves over the following weeks and months. And choosing the wrong one for your situation is where a lot of QC programs quietly go wrong without anyone noticing. A fixed mean is exactly what it sounds like. The number calculated once, early in the lot's life, stays untouched for the entire time that lot is in use. It's simple and highly stable, but it also means normal, expected long-term instrument drift over months can eventually make every result look artificially borderline. A cumulative mean takes the opposite philosophy from a fixed one. Every new point folds into a continuously updated running average, converging toward a very stable number over time. A floating, exponentially weighted average goes further still, deliberately giving recent points more influence, so genuine drift shows up faster, at the cost of chasing more day-to-day noise. The statistical intuition behind why n equals 20 was chosen as a floor becomes visible when you plot estimated SD against sample size. The estimate swings wildly with only 5 to 10 points, tightens noticeably by 20, and only creeps marginally tighter beyond that. Exactly the diminishing returns curve the standard error formula predicts. Plotted side by side against the same 60 days of real data, the difference is visible immediately. The fixed mean stays perfectly flat, the cumulative mean drifts very gradually, and the EWMA line visibly bends to follow a genuine slow upward trend within the first 2 to 3 weeks of it starting. There's a fourth tool worth knowing even if it's used less often: robust statistics, using the median and median absolute deviation instead of mean and SD. Because the median isn't pulled around by extreme values, a robust baseline resists distortion from the occasional wild outlier far better than a conventional mean or SD calculation. So which method fits which situation? A brand new instrument or a lab still building confidence in a method benefits from the stability of a cumulative mean. A lab with known slow reagent degradation between lot changes may deliberately choose an EWMA approach specifically to catch that drift earlier. None of these three methods is inherently correct or incorrect. They're different tools solving different problems, and the real skill is picking the right one deliberately rather than inheriting whatever the LIS happen to default to. That same decision becomes unavoidable every time a QC lot changes. QC material doesn't last forever. Every lot has an expiration date, and a fresh lot needs its own baseline before the old one runs out. The transition window between an expiring lot and its replacement is, by a wide margin, where most baseline confusion actually originates in real laboratories. The core technique is parallel testing. For roughly 20 to 30 days before the old lot expires, both the outgoing and incoming lots get run side by side on every shift. The outgoing lot continues driving daily QC decisions as normal, while the incoming lot silently accumulates its own independent 20-point baseline. Different lots of the same control material are not guaranteed to have identical target values. Manufacturing variation between lots is normal and expected, meaning a healthy, well-functioning instrument can legitimately show a new lot centered at a genuinely different number than the outgoing lot, with no analytical problem at all. This is exactly why you never simply carry the old lot's mean and SD forward onto a new lot's chart, even though it's tempting when the new lot looks about the same. Each lot earns its own independently calculated baseline, built from its own 20-point minimum every single time. A real-worked example: an outgoing lipid control lot has a documented mean of 185 milligrams, or DL. The incoming lot's 20-point parallel data centers on 179 milligrams, or DL, a real, expected, and entirely acceptable lot-to-lot difference of about 3%, well within what manufacturing variation predicts. The cutover itself should be a documented, deliberate event, not something that happens quietly because the old bottle ran dry mid-shift. The exact date, the outgoing and incoming lot numbers, both sets of mean or SD values, and the technologist who verified the transition all belong in the permanent QC record. Skipping the parallel period entirely, simply switching to a new lot's insert values on day one with zero lab-specific data, is a genuinely common shortcut under staffing pressure, And it's exactly how labs end up running weeks of QC against a target their own instrument has never actually demonstrated. Done properly, a lot transition is boring, a quiet, overlapping, well-documented handoff where nobody notices the exact day it happened. Done poorly, it's exactly the moment a lab's QC chart silently disconnects from what the instrument is actually doing. Here's the single most dangerous mistake in this entire topic, and it usually comes from good intentions. A technologist sees repeated QC flags, gets frustrated, and simply recalculates the mean to match whatever the instrument is currently reading, making the flags disappear without ever asking why they appeared. Quick pause. If this breakdown is helping you, take a second to hit like and subscribe. It genuinely takes a lot of effort to make videos like this, and your support keeps them coming. This practice has a name among QC specialists: chasing the mean. Each time the target is nudged to match the instrument's current output, any genuine systematic drift gets silently absorbed into the new normal, which means the QC chart stops being able to detect the very problem it exists to catch. Visualized over months, the effect is striking. A true, uncorrected instrument drifting slowly downward on a fixed baseline would trigger clear Westgard rule violations partway through. On a chased mean that keeps sliding to match the instrument, the exact same underlying drift produces a flat, reassuring-looking, completely misleading chart. The patient safety consequence is not abstract. If the drift being masked reflects genuine calibration decay, a failing reagent lot, or a probe delivering an increasingly inaccurate volume, every patient result reported during that window is drifting right along with it, invisibly, because the chart that should have caught it was quietly reset. The clean rule that separates a legitimate baseline update from mean chasing is simple to state, if not always easy to follow under pressure. A documented, known cause must come first. New lot, verified calibration, documented reagent change. Those justify recalculating a mean. An unexplained drift never does, on its own. CAP and CLI inspectors specifically look for this exact failure mode during accreditation surveys. A QC mean with an undocumented, unexplained history of frequent recalculation is treated as a genuine red flag, not a paperwork technicality, precisely because of what it usually indicates. The practical safeguard is procedural, not just cultural. Any proposed baseline change should require a documented reason, a supervisor's sign-off, and a brief investigation note. Friction that's deliberately inconvenient enough to stop a rushed, frustrated just reset it decision at 2 a.m. on a busy shift. So the goal was never a chart that always looks perfectly in control. It's a chart that accurately reflects reality, flags real problems when they occur, and gets updated only when there's a genuine, documented reason to. Which raises the obvious next question. How do you actually tell the difference? The question, is this a real shift or just noise, has an actual statistical answer, not just a judgment call. And the tool most labs already have access to but underuse is the standard deviation index, a single number that translates any drift into directly comparable, interpretable units. SDI turns an awkward question, is 2 milligrams or DL a big deal for this analyte, into a standardized one. An SDI under 1.0 is generally considered good agreement. 1.0 to 2.0 warrants attention, and anything above 2.0 signals a systematic difference from peers worth investigating before it's dismissed as normal variation. A worked SDI calculation. This lab's cumulative sodium mean sits at 141.2 mol, or L. The peer group using the identical instrument and method averages 139.8. with a peer group SD of 0.9. That gives an SDI of exactly 1.56, inside the warrants attention zone, not yet a clear systematic problem. SDI answers, how different from peers, but it doesn't by itself answer, is this getting worse? For that, Westgard's own multi-rule framework remains the frontline tool. Specific rule violation patterns point towards specific underlying causes, which is exactly what turns an alarm into an actionable next step. That drift pattern distinction is exactly why 4_1s and 10x violations are the ones most often mistaken for a legitimate reason to simply reset the mean. They look like a genuine trend, and sometimes they are one, but the correct first response is still root cause investigation, never an immediate recalculation. A practical investigation checklist. roughly in the order most labs work through it. Verify the control material itself wasn't mishandled or expired. Check for a recent calibration or maintenance event. Review the reagent lot number and its expiration, and confirm the environmental conditions. Temperature, humidity haven't shifted. Only once a specific, documented cause is identified and corrected does recalculating the baseline become the right move. And even then, the recalculation uses fresh post-correction data, not the drifted data that triggered the investigation in the first place. SDI tells you how far off you are from everyone else. Rule patterns tell you what kind of problem you're likely looking at. Root cause investigation tells you why. Only all three together, not a gut feeling about a chart that's been flagging too much, justify actually moving the baseline. Let's walk one QC lot through its entire life cycle, start to finish, with real numbers at every step. The same sequence that should play out on every analyte, every lot, in every lab running a properly managed QC program. The new lot's 20-point parallel data produces a preliminary mean of 9.85 milligrams or DL with an SD of 0.18. Noticeably close to the outgoing lot's documented 9.78 milligrams or DL, a small, expected lot-to-lot difference well within normal manufacturing variation. So the cutover proceeds as planned. 30 days into routine use on the new lot, a 4_1S pattern appears, for consecutive results sitting above the mean, each one slightly higher than the last. It isn't a dramatic violation, but it's exactly the trend pattern that deserves investigation rather than either dismissal or an immediate baseline reset. Working the investigation checklist in order. The control materials storage log shows no issues, but the maintenance log reveals a probe calibration was performed 6 days before the first elevated point. A documented, dated, plausible cause that lines up cleanly with when the trend actually started. With a documented cause in hand, the lab collects 20 fresh data points after the calibration event, not blending them with the pre-calibration data, and calculates a new post-calibration baseline. Mean 9.94 milligrams or DL, SD 0.16, formally replacing the prior working target with full documentation attached. This entire sequence, new lot, parallel testing, preliminary baseline, a legitimate trend, a documented cause, a justified recalculation, gets recorded as a single continuous QC record, exactly the kind of paper trail a CAP inspector expects to be able to follow from beginning to end, without a single unexplained gap. Notice what never happened anywhere in this sequence. Nobody adjusted the mean just because a chart looked unhappy, and nobody blended contaminated pre-problem data into a fresh calculation. Every single number change traces back to a specific, dated, investigated cause. That's the entire discipline in miniature. Establish carefully, transition deliberately, investigate before adjusting, and document everything along the way. None of it is complicated in isolation. It's simply a lot of small, correct decisions that most confusion in this topic comes from skipping. None of what's been covered is one lab's opinion. It's built directly on CLSI C24, the formal guideline governing statistical quality control for quantitative measurement procedures, alongside CLIA and CAP accreditation requirements that inspectors actively check against during every survey. It's worth tracing where this entire framework actually came from. Walter Shewart built the original statistical control chart for industrial manufacturing in 1924. It took until 1950 for pathologists Stanley Levy and Elmer Jennings to adapt it specifically for the clinical laboratory, the chart every lab still uses today. One detail from that history is a nice bit of trivia worth knowing. In the earliest clinical adaptations, QC material was actually called standards, not controls. The modern terminology only settled in once serum pools replaced patient samples as the material of choice, decades after Levy and Jennings' original 1950 paper, bringing every principle together into a single reference, established with a genuine 20-point minimum. Transition lots through documented parallel testing. Choose your ongoing mean update method deliberately, never adjust without a documented cause, and use SDI alongside rule patterns to separate real shifts from noise. Applying Six Sigma thinking to this whole discipline gives one final useful lens. A lab whose baseline management consistently follows this sequence: proper establishment, documented transitions, cause-based recalculation only, measurably reduces false rule rejections, which is itself a direct, quantifiable sigma metric improvement. For any lab auditing its own practice, 3 honest questions cut straight to the heart of it. Can you trace every baseline change on file back to a documented cause? Is your current chart centered on your own data, not a stale insert value? And was your last lot transition actually run in parallel, or just switched cold? None of this requires new equipment, new software, or a bigger budget. It requires exactly the discipline of doing the 20 points properly, documenting the transition, and resisting the very human urge to just make an annoying flag go away without asking what it was trying to tell you. The mean on a QC chart isn't a number you pick. It's a number you earn through proper data, honest documentation, and genuine investigation every time it needs to change. Get that discipline right, and one of laboratory medicine's most confusing topics stops being confusing at all. Here are the key references and sources for this video. Thanks so much for watching. If this helped, like the video and subscribe for more clear, simple explainers, and I'll see you in the next one.